So again, my name is Scott Lytle. I'm the chapter chair for the IEEE EMC Society here in Southeastern Michigan. And I thank you for joining our Zoom meeting today. As you know, it was originally scheduled to be an in-person meeting, but our speaker came down with an illness, so he was unable to travel to Michigan. So he's feeling a little bit better now, and he decided we can still go ahead with our Zoom meeting this evening. So I'd like to thank you all for attending. We have about 43 people had signed up last time I had looked. And because this is a Zoom meeting, we send out the announcement to some of the sister chapters across the country. And I noticed we have people from California, Minnesota, Illinois, as well as here in Michigan. Um, if you stay through the whole meeting, afterwards, we're going to have a drawing, and we're going to give away 3 Amazon gift cards for $25, $50, and $75. So if you want to stick around, you must be present to win for that. This evening, our presentation is going to be by Louis Feudi of Raymond EMC, and his topic tonight is design characteristics and verification of chambers for testing to CISPR 16, sVSWR, and low frequency magnetic fields. Louis has been a product safety, an EMC, telecom, and Belcore engineer, engineering manager, salesperson, a sales manager, and corporate trainer. Lou has worked in Underwriters Laboratories, Intertech, TUV Rhineland, and U.S. Technologies. Lou has also been a global and U.S. sales channels manager, selling equipment for Keytech and Thermo Fisher Scientific, as well as TESEC and Ametek. Lou has a total of 43 years of experience in the compliance testing industry and has authored a number of articles for Compliance Engineering and In Compliance magazine. Lou is currently the U.S. sales manager for Raymond EMC, the Anechoic and semi-anechoic chamber, reverb chamber, and shielding enclosure manufacturer. Louis.
Yes, Scott, I'm on.
Okay, great.
Thank you.
You
And
can
thank you
turn
for
on
the
your camera
introduction.
or slides or whatever you'd like to do. I'm going to disappear for just a couple minutes, but I'll be right back.
Not a problem. I'm going to share my screen.
I think I still have you as co-host. Let me double check. Make co-host. Okay.
Yeah, it looks like it's sharing.
Okay. Very good.
Good evening, everyone. First, I'd like to apologize once again for not being in person. I was really looking forward to seeing everyone. Although it is January in Michigan, I do actually enjoy flying up there and attending your meetings. So it's hopefully I'll be able to do it again next year. And I know Candace always likes that I do it on January, so I'll do it once again if I can. In the meantime, however, I wanted to take a few moments to thank everyone for giving me the opportunity to speak today. To let you know that once again, I work for Raymond EMC. We're a manufacturer of chambers and a number of shielded enclosures, reverb chambers, CISPR 25, CISPR 16, Mill Standard 461, DO 160, pretty much any type of chamber that needs a requirement for testing. We are able to provide, build with partners like TDK, RF Solution absorber material, or DMOS material. We have a number of different suppliers so that we're not limited to any one particular type. And if there's ever any need for anyone to have anything, you're always welcome to contact me. In the meantime, however, let's get started. As I've said, I've done this before. And one of the ones I've done before was the NSA requirements for CISPR 16. And in order to conduct the sVSWR and the low frequency magnetic field testing requirements, I'm going to do a brief review of CISPR 16 NSA requirements as well. Please forgive me if I stutter or pause. My mind is still a little fuzzy from the COVID, but for the most part, I believe I'll be able to get through this in a reasonable amount of time. One of the things to remember with regard to NSA is that a weather protected or fully enclosed OATS or semi-anechoic chamber, instead of a single point aspect where you're measuring just from the center of the turntable to the receive antenna, in order to verify that the chamber or the open area test site is operating properly, when you enclose it in any manner whatsoever, and use construction material to enclose that ground plane test site, then the standard indicates that it's possible that the results of a validation measurement at any single location may not be adequate to show acceptability of an alternative site. Such being the case, any single measurement is insufficient to pick up the possible reflections from any material surrounding the OATS turntable, or in this case, the walls and ceilings of a semi-anechoic chamber. So the standard defines a test volume, and that test volume is traced out by a EUT rotated 360 degrees, and the standard requires that you take up to 20 measurements in order to determine that the volumetric measurement that you're taking is sufficient to qualify the site that you're testing. Now, we talked about OATS in the last presentation. It's probably still on file within the organization, so it's probably available to you. If not, I can always send a copy. However, this is going to be specific to shielded enclosures and enclosed chambers because it requires the volumetric measurement. Volumetric measurement has 20 measurements because you are actually taking measurements where your transmit antenna is located in the center of the turntable, at the forward lip, the left lip, the right lip, and the rear lip of the turntable, or whatever it is that you want to decide to determine to be the size of your quiet zone. And that's what the volumetric measurement, that's what the approved volumetric measurement is called, is the quiet zone. So by taking those 5 transmit antenna locations and taking them with both a horizontal and vertical polarization of the both transmit and receive antennas, and then also taking it at 2 heights of the transmit antenna, 1 meter and 1.5 meters for a horizontal polarization, and 1 meter and 2 meters for the vertical polarization, you wind up with 20 measurement positions for each frequency that you're measuring. This gives you an example of copolarization where both the biconical antenna is located in the vertical position, and then you do it again in the horizontal position, and the multiple positions are located on different points of the turntable, whereas the receive antenna is pretty much located in the same spot. You just simply move it forward or back so that you're always measuring a distance of whatever it happens to be, 3 meters, 5 meters, 10 meters, depending on the NSA measurement that you're making. But the transmit and receive antennas moved to maintain that test measurement, as I just said. For the SAC, we have to make sure that the horizontal measurement, that you have a spacing of 25 centimeters between the antenna tip and any cone tip nearby. For the vertical measurement, we need to make sure that the lowest point of the antenna, or the tip of the antenna, is at least 25 centimeters above the floor. This is to prevent coupling with the ground plane. Even if the center of the antenna is higher than 1 meter, this 25 centimeter clearance takes precedence. And for weather enclosed sites, the edge of the turntable is usually selected as the width of the test volume, as I mentioned earlier, with a 2-meter height. I'm going to open my page here in case anybody has any questions. If you'd like, you can wait until the end of the presentation, but if anything is urgent that you may need to ask, I will hopefully be able to see all of you and raise your hand if, or indicate the hand raise if you have one. This shows the positioning of the transmit antenna on the turntable or in the quiet zone: center, left, right, forward, and rear. And again, it shows the receive antenna. The receive antenna is actually turned towards each of the antennas so that you get a clear measurement. And at the same time, it is also moved forward so that it covers the back end, so that there is a measurement distance of D, which is either 3, 5, or 10 meters, depending on how you're qualifying the site. And then it's moved up again to the front which brings it back here. And that again allows you for that distance D. And in the center, it's manufactured with the center portion here. I should say it's conducted with the center portion here, with the center of the turntable. Again, this is a review material from another presentation. However, should be able to move on this right now. Did someone have a question? No? Okay, I'm sorry. Okay, now, once the standard provides a theoretical normalized site attenuation, and what it's done is basically, if the ground plane was an infinite ground plane with no reflective material around it whatsoever, so you had basically a perfect open area test site location, these theoretical normalized site attenuation measurements or values is what you should expect to meet or measure when you conduct the testing. And we're going to go through the steps of testing very quickly, which is on the next page, in which you take a direct measurement by basically measuring the voltage value at the terminal of the transmit antenna. You connect your cable to the cable that is going to the transmit antenna, and you take a measurement. And then once you've gone through the entire frequency range, taking that measurement and recording the value with a known transmit value, you repeat those transmit values through a transmit antenna and a receive antenna, which is what the V site measurement is. And then taking into account the antenna factor for the transmitter antenna and the antenna factor for the receive antenna, if you take the direct measurement and you subtract the site measurement with the adjustments for the antenna factors for both the transmit and receive antennas, then you wind up with A sub n, which is the theoretical NSA, and that value should be equal to the AS, or should not be more than plus or minus 4 dB from that value. So once again, you take your measurement, you compare your measurement by, again, taking the direct, subtracting the site, accounting for modifications by the antenna factors, and then comparing it with the value that is the theoretical value, and that delta with that theoretical value should be plus or minus 4 dB or less when doing your measurements. This is an example of a test volume. Again, for the horizontal, you take a measurement at 1 meter and 1.5 meters and in height, and for vertical, you take 1 meter and 2 meters in height. And this gives you an indication of what the test volume looks like inside the chamber. Again, in this case, we're looking at a 2 meter quiet zone, 3 meter measurement distance, and we've got our spacings according to the standard that allows for the turntable, excuse me, the location of the turntable, which allows for the quiet zone to be located within the chamber, and again allows for the measurement distance necessary. This is a vertical view, and as you see, there's also absorber on the floor. This is for sVSWR, but for NSA, there is no absorber on the floor. You take advantage of the situation with regard to a ground plane to maximize the emissions that are coming off of the chamber or within the chamber and what's coming off of the product that's on the turntable. So you do it without a ground plane, but when you do sVSWR testing, you do add the absorber on the floor, which leads us to our sVSWR, or site standing voltage wave ratio. Now, what we did just now was check to see whether there was a value that we are able to measure in comparison to a theoretical value for NSA, and then did a measurement as to what the delta between those two values were, and it could not exceed plus or minus 4 dB. The sVSWR is actually exactly what it says. It's a ratio. It is a ratio between a number of measurements that you take, and what happens is that there's a variable height receive antenna that's located at the specified distance, which could be 3, 5, or 10 meters again, from a variable height transmit antenna. The transmit antenna is located at the center of the oats. It's also at the left position, the right position, and the front position. It does not go to the rear position. The broadband antenna method is used, and as a result, you use two copolarized antennas, as we mentioned earlier. Usually you'll have a biconical up to 200 megahertz from 30 meg, and then from 200 to 1 gig you have a from 200 to 1 gig you have a log periodic, and then from 1 gig and above it's usually a horn antenna, and you're operating on a 50 ohm system. These are the locations in which sVSWR testing is conducted, and in this case you're not changing the positioning of the receive antenna. You don't actually point it at the locations. You keep it in a simple or standard point, but you are measuring to each of these points accordingly. And these are defined specifically in the standard. And what you're doing is you're taking a measurement at the, let's say at the edge on the right side, and then you're taking one a little further away, a little closer, a little closer, a little closer, a little closer each time. And those values are specified in the slides that I'm going to show you on the next few pages. And then you normalize each one of these to the distance factor. And as a result, you then check to see if there's less than a 6 dB difference between any of these items when each of these measurements are normalized to the original measurement distance of 3 meters, 5 meters, or 10 meters. So in this case, front position 1 to 6, or F1 to 6, F6, is the front positions are on a line in the center of the test volume to the receive antenna reference point. You locate the first one at the point, and then you subtract distance to move it closer and closer to the receive antenna. Excuse me, away from the receive antenna. So you go F5 to F1 are measured where F1 is F6 plus 40 centimeters, F2 is F6 plus 30 centimeters, F3 is F6 plus 18 centimeters, F4 is F6 plus 10 centimeters, F5 is F6 plus 2 centimeters, and F6 is the actual value we were looking at earlier. So that would be right here. So moving forward again, we're taking 6 measurements at varying distances, starting at the distance that you were supposed to measure to the edge of the front edge. And then again, you're moving it away from the receive antenna to try and get a better value, or get another value that you're measuring. And each value that you take is still normalized. It's put into a function, a mathematical function, which normalizes it as if you were measuring at the same distance of F6, which is the original measurement distance. The same is true of all of them. Here's positions 1 through 6, for example. Again, the site measurement distance itself is F6, and then you move it further and further away until you're 40 centimeters away. Same is true for the right position, 1 to 6. The left position, L1 to L6. The center position of C1 to C6. And those 4 distances are what is measured. In addition to that, if there is a certain height application with regard to the standard that calls out, then you might take a top of the test volume may be required as well, depending on the height of the test volume. We'll show the additional height restriction requirements for sVSWR measurements in a slide or two under figure 24, but to give you an indication, if the height is 1 meter above the bottom of the volume, that's your right standard volume. If H2 is the top of the volume, and it gives an indication that if, I believe, H1 and H2 is greater than 0.5 meters, the difference, then you take H2 as well. Otherwise, you simply take H1 in the bottom. Those two are required in order to do the testing. Excuse me, I'm sorry, just take H1. You don't take the bottom. H1, and then if it's greater than 0.5 meters above, then you take H2 as well. So this is a flow chart that's in the standard that gives you an indication as to what tests you need to do. And again, you measure the forward position at the first height with 1 horizontal through F6 height 1 horizontal measurement, and you do F1 height 1 vertical measurement through F6 height 1 vertical measurement, and plugged into the standard or plugged into the formula, which we'll be going over. If it passes, then you move on to the left and the right. If those fail, then you have a failure. However, if any of these fail, it's a failure. However, if they all pass, then you check to see whether the test volume diameter is greater than 1.5 meters. If it is, then you have to do the center measurement as well. If it is not, you don't have to do the center measurement. Then you'll check to see whether H2 is 0.5 meters or more higher than H1. And if it is, then you do your second height measurement of F1 through F6. And then if that passes, then you've passed your testing for sVSWR. This just gives another, excuse me, excuse me one moment. I'm sorry. This chart gives the table of the measurement position designations. And again, as we've talked about, F1 is the front. H1 is your first horizontal measurement through F, and you have, excuse me, the reference position for those equations, or that the dereference equation, which we've all gone through so far. All the items I've gone through for you so far is coming out of this chart. Once we then have the procedure itself, and basically you're getting points M, N, O, P, and Q, which are the measurements that you're taking from each of those values. The reference measured signal M is the received electric field strength or voltage measurement at each position, depending on whether you're using a spectrum analyzer or something else. And it's similarly denoted by subscripts as M, N, O, P, and Q, M, which is measurement. So for example, P, F1, H1, H, which is F1 position, height 1 position, horizontal is the position F1 at height 1, horizontal polarization, and its measured signal is referenced as MF1H1H. You locate the transmit source in the position that you want to take. You locate the receiver antenna a distance D, which is the measurement distance, 3, 5, or 10 meters. And you note that the receive antenna height shall be located at the same height as the transmit source. Then you verify that the receive signal displayed will be at least 20 dB above the ambient noise so that you're getting a clear signal. You record the measured signal level at each frequency, and you can sweep measurements. Then you repeat steps B and C for each of the other locations. So there's 6 measurements for front, 6 measurements for center, 6 measurements for left, 6 measurements for right. Change the polarization to vertical. Repeat the tests again for all 6 measurements for each location. And then for all measurements, you normalize the measured field strength. And this is very important. You normalize the measured field strength or the voltage data to the distance of the reference position shown in Table 7. So as we mentioned earlier, Table 7 showed that there was plus 10 centimeters, plus 18 centimeters, plus 30 centimeters, plus 40 centimeters. Each of those have to be normalized to the reference position. And in order to do that, you use equation 23, which is located right here, which is M prime, which is a normalized value, is equal to the value that you measure, plus 20 log the distance measured over the distance reference. Basically, what you're doing is you're adding that 20, 40, 60, 70, 80 centimeters, and you're normalizing your value that you're measuring to as if it was at the exact distance rather than with those added items. And then knowing that, you use this equation to calculate the sVSWR for the horizontal polarization, using equation 22 as well. 23 normalizes your value to the distance that you're measuring at, which is F1, H1H, F2, H1H, F3, H1H, F4, F5, all the way up to F6. And then you use equation 21 or 22 to see whether your sVSWR is correct or not. It should fulfill the acceptance criteria 732, which we'll go through, and I'll go through equations 22 and 23 in a moment, or 21 and 22, excuse me. And then you repeat those steps for all the other segments of the test volume. And repeat again at the center position or at the second height if required based on that flow chart that we showed earlier. These are equations 21 and 22. And the sVSWR is basically the ratio of the maximum receive signal to the minimum receive signal. So you take your maximum value and your minimum value, and you do a comparison. You do a ratio. You divide the larger from the smaller. Whether it be Emax or Vmax being the receive signal, or if you're using a spectrum analyzer for the voltage. For the procedure that follows, dBs are typically used for the measurements and calculations. And if that's the case, then sVSWR in dB is equal to 20 log Vmax over Vmin, or 20 log Emax over Emin, which is basically Vmax in dB minus Vmin over dB. And basically that value, when measured and run through this formulation, should be either 2 to 1. It's not showing, is it? Why is it not showing? All right, I'm sorry. It should be 2 to 1 for, something's wrong with my slide for a second. The results are not showing, but basically the ratio should either be 2 to 1 or the 20 log Emax minus Emin or Vmax minus Vmin should be equal to less than 6 dB. I'm going to stop this for just a second and see if we can drop down to that one. There we go. So can everyone still see this? I guess you could, because I still see I'm sharing. So your sVSWR is either less than or equal to the 2 to 1 ratio, or your sVSWR in dB, as we mentioned in equation 23, is less than or equal to 6 dB. If you meet this specification using F1 through F6, R1 through R6, L1 through L6, C1 through C6 if necessary, and H1 and values at H2 if necessary, and they all meet this specification, then your chamber is, or your open area test site, or your shielded or enclosed open test site or semi-anechoic chamber is considered to be compliant with sVSWR specifications. At this point, we're going to then move into CISPR 16, magnetic field emissions. Now, all we've ever had to do in the past is NSA and sVSWR in order to qualify a volumetric measurement on a open area test site with the weather enclosure, for example, or on a semi-anechoic or fully anechoic chamber. All we've ever had to do in the past is NSA and sVSWR, and those were values between 30 megahertz and 1 gigahertz for the NSA, and 1 gigahertz to 18 gigahertz for sVSWR. However, starting in February, new requirements are expected to go into effect that were published in CISPR 16, which will require that the site be qualified under magnetic field performance requirements from 9 kilohertz to 30 megahertz as well. And it's very, very similar, if not almost exactly similar, and I say exactly similar, but exactly the same as the NSA requirements that we talked about at the very beginning of the presentation. From 30 meg to 1 gig is plus or minus 4 dB. The sVSWR performance requirements we talked about from 1 to 18 is less than or equal to 6 dB. And the magnetic field requirements are now from 9 kilohertz to 30 megahertz and should be either plus or minus 4 dB from the ideal theoretical value, which is given in the standard. So we go through the same measurement procedure for the most part that we did for NSA. CISPR 16.1.4 includes updates to test site validation in the 9 kilohertz to 30 megahertz range for both normalized site attenuation loss, insertion loss, and reference site method. We're going to go through the normalized site insertion loss requirements. It's done at either 3 meters, 5 meters, or 10 meter test distance, and it involves 2 magnetic loop antennas placed at a 1.3 meter height with measurements done in the X and the Y and the Z orientation. So a minimum of 345 separate frequencies, which are called out in the standard, are required to be measured. And the insertion loss deviation, again, must be plus or minus 4 dB to pass validation for all test locations and frequencies. And once again, we are looking at our turntable, and we are looking at the center, front, left, right, and rear, same as we did with NSA. We're moving the antenna forward in order to catch the back end of the turntable. We're moving it back to catch the front surface of the turntable, and we're, excuse me, we're leaving it in the center of the turntable with our measurement distance D for 3, 5, or 10 meters. Oh, excuse me. This is done in both the X, the Y, and the Z axis applications at a specified measurement distance, which was called out earlier, 1.3 meters. Once again, the deviation or the insertion loss deviation is equal to a measurement of a direct value, which is taken directly as a conducted measurement across the frequency range. You subtract the site measurement value, which is the value that you measure from the receive antenna with the transmit antenna connected to the cable prior to or after you've taken the direct site, which between the transmit and receive antenna cables are attached together. You take your direct measurement, then you take your site measurement between the antennas, and then you subtract your electric field antenna factor, or excuse me, your magnetic field antenna factor of the transmit antenna, the magnetic field antenna factor of the receive antenna, and then you compare it against by subtracting the normalized site insertion loss value, which is calculated in accordance with Annex J, and that gives you the site insertion loss deviation. So this is very similar, as you can see, if not exactly similar or exactly the same as the NSA, using just instead different values and different locations and different antennas. CISPR 16-1-4 Edition 4 amendments are active publications. It is unclear if NSIL testing is currently required, but it is being offered as a test service by providers like, for example, SIS, who is a ISO 17025 accredited calibration organization. Edition 5 of CISPR 16 will be published in February 2025, which will include the new testing requirements. However, that does not necessarily mean that it will be required in February of 2025. Once it's published, I'm sure we'll have a better idea, if not prior, as to what the actual time will be required to get the chamber calibrated and in compliant, if not already, with the new valid publication. We've had some of our partners looking into this, and so far, many of them have come back preliminary results saying that there won't be any major modifications necessary to meet this, as long as the ferrite is sufficient for the value. And we have not yet gotten a full answer on that yet, but we are in the process of looking into it right now, and we plan on having that information available to our customers hopefully by the end of February. With that, are there any questions that I might be able to answer?
So Lou, this is Scott.
Yes, Scott.
So I guess my question was, I think you already kind of covered a little bit, at what point do you think the auditors, the laboratory auditors for ISO 17025 would require this for, I suppose, the magnetic addition? Is there any thoughts on that yet?
There's no feedback that I've received so far as to when it will be going through yet. I welcome anybody who might be sitting in a committee for this to chime in. However, the people I've spoken with so far have said that they're not quite sure when it's going to be implemented. It will be published in 2025. Usually, once the standard is published, it is then published in the official journal of the European Union. Once it's published in the official journal of the European Union, it either becomes effective immediately or there's an effective date provided as a result of the publication in the official journal of the European Union. So right now, we don't know when that date's going to be. What we do have so far from feedback from our as I said, our suppliers of absorber and ferrite and design of the chambers themselves is that there's not going to be a major qualification that they're aware of so far that may have an impact once this goes into play.
Steve.
Jamal, you have a question?
No, sorry.
Okay. Any other questions?
Hey, Lou, this is Larry. I did have a question. In your experience, what are the major variables in the chamber that contribute to non-compliances to these checks that you described?
Well, for NSA, it's usually ground plane issues. If there is not good ground connection, for example, between the turntable and the ground plane, if there are hatches located in the path of the measurement, usually they're located somewhere adjacent to the turntable or to the mast or even in between, where the sides of the edges of the panel for the floor panels are not making good ground connection. Excuse me. That could also cause issues. If the absorber is not properly set up on the walls and ceilings, and when I say that, I mean that sometimes there are different size absorber depending on sVSWR and NSA and location behind the turntable itself. That could usually have an impact on whether the quiet zone is impacted. Ensuring that there's sufficient space between the antenna and any point or the points of the absorber adjacent to the receive antenna, as well as sufficient space behind. Usually, at least a meter is what we try to put in between the rear end of the turntable and the back wall. Those are some of the items that we've seen. What we usually see on a semi-anechoic chamber is that there's full lining of ferrite on all four walls and ceiling, and that there's either specular regions on the absorber locations, or they can have a fully lined. We don't see much of a difference between fully lined and not with regard to this type of application. If you are also using your chamber, for example, from MIL standard 461 or DO160 or CISPR 25, then fully lined walls and ceilings come in handy because you can pretty much pick any wall you want in order to go ahead and do your testing. But for EMC testing to CISPR 16, specular regions are more than sufficient. But those are some of the items that we've come across so far, is usually the ground plane. We would also want you to check, or you should also check, cable connections, connectors, bulkhead panel connectors as they penetrate the bulkhead panels, to ensure that they're grounded properly, that they're not loose, that you don't get any intermittent noises. Location of the turntable with relationship to the door has some impact sometimes too, unless the door has a full cones on it as well, if it's adjacent to the turntable, in which case there's no reflection and no impact on the measurement taken. So there's a number of items that can be looked at that could have a possible impact excuse me, on the chamber performance. Does that answer your question?
Yeah, very good. Thank you. Appreciate
No
that.
problem. No problem. Any other questions?
I guess so. Just one general question: does
Sure.
EMC chamber, the sprinkler system, the electrical system, do they affect this measurement?
I'm sorry. Could you repeat that just a little louder?
The sprinkler system, right? You have like fire protection, right?
Yep.
And you have electrical conduits and wirings. Those are within
Sure.
the. Do those have an impact on this measurement?
They could. What we usually do is route electrical. Well, one of the great things about an EMC chamber is that we usually put in a raised floor, and the raised floor allows us to run all the electrical systems below the floor. And it also allows you to have a pit which also allows you to have a raised turntable, which could be level with the floor, and at the same time still have a motor below it to operate it. So with the incorporation of a raised floor in the chamber, a lot of the electrical aspects and the grounding aspects go away. However, if you are running your chamber for any reason and you're using, for example, a surface turntable, then you have to make sure that the motor does not have any impact on the operation of the measurement. You have to make sure that it's quiet as well, because it's no longer located below the ground plane. You have to worry about running your electrical conduit in the corners below the cones and the ferrite. So a lot of the time the electrical will go in before the ferrite and cones go on the walls. But at the same time, if you're using a raised ground floor, a lot of that issue goes away. With regard to the fire protection, excuse me, excuse me. With regard to the fire protection, as long as there's no major reflection that can have an impact, and most of the time you're looking at very small heads, and usually the measurement is taken while the fire protection values are either non-telescoping, or if they do telescope, obviously then there's no measurement taken. So as long as they are embedded in the cones, but can telescope out, or as long as they are at a level of the cones, but don't provide a significant reflection, very often they won't have an impact on the testing. And also we try to locate them outside of any specific reflective zone. Remember that we're always looking at reflections from the center of the turntable and the location from the quiet zone, where it may bounce off the walls, and the angle of reflection should be wherever there's an angle of reflection, it will take it back to the receive antenna. There's some kind of cones and absorber in that location. Putting the materials like the fire protection sprinkler heads outside of that conical zone, or outside of that zone, so that any reflection off of it does not work its way back to the receive antenna, usually will not have any impact on the measurement that you're taking.
Thank you.
No problem. Any other questions?
Yeah, I have one more question, this is Larry.
Hi, Larry.
As far as the duration of time between these measurements, is this something that you only do when the chamber is first constructed, or is there any requirement from an audit situation where you would have to repeat this measurement on a regular basis?
When I worked as a operations manager at U.S. Technologies in Georgia, we had our calibration at that time through NavLab. But I believe that both NavLab, A2LA, and a number of other accreditation organizations require that this testing be, or that the accreditation for the standards that you're evaluating to and the materials that you're using to evaluate to that standard through the 17025 calibration should be done every 2 years. You resubmit data. In the meantime, however, one or two things that you might want to consider is testing at least once a year, but you could go to 2 years on it. It's 2 years is usually required in order to maintain or renew your accreditation. The other item too is that there should be some tests that are done on a daily basis. Like you should check your cables every day to ensure that there's no cable loss difference. You should have a generator, a comb generator, for example, on site at a certain location on the site or in the chamber, and run a quick scan through a comb generator to get a consistent reading every day, to give you an indication that there's nothing really out of the ordinary on the readings that you're taking. That would give you an indicator that if you did see anything that was wrong, in good practice, if you did this every 3 months and you're a testing laboratory, for example, that does this on a daily basis with a numerous number of products, and you find out at the end of that 3 months that there was an issue, and you go back and find out that there was a problem, then everything that you tested for the past 3 months has to go back and get retested again. So doing it on a daily, just a quick double check on both the cable and on the comb generator is a good idea. And then you should do this a minimum of once every 2 years, but more like once a year is a good idea. That answer your question?
Yep. Thanks, Lou. I appreciate that.
Anytime.
There's a really good standard that Matt Jackson from Denso worked on that talks about statistical process control.
Yep.
And I think that's also beneficial to take into account when you're looking at your calibration cycles.
Historically, I've seen situations in the past where something was not tested periodically, except maybe once a year, for example. From, and companies like Cisco used to have 5, 6 internal laboratories running a day doing testing. And if they didn't check this stuff on a daily basis, they could have numerous products that they would have to go back and retest or recall. So it's always a good idea to have some kind of a spot check on a daily basis, and then a confirmation check at least once a year, and as required, once every 2 years in order to be able to do the testing and maintain your accreditation. Any other questions?
Size of the chamber affect these measurements.
I'm sorry, can you repeat that?
I was just wondering how the size of the chamber, whether it's 3, 5, 10 meter, affect the measurements. These measurements.
The size of the chamber is dependent upon the size of the quiet zone. We have to build chambers in accordance with what the customer needs from a quiet zone aspect. So one of the things we do when we're quoting a chamber is that we ask for the equipment under test size, which we can then help to determine the quiet zone size. And once we know the quiet zone size and we know the performance specification as to whether you want to do plus or minus 4 dB, or some manufacturers or test organizations or testing laboratories like to see if they can drop it down to 3.5 or even 3 as their maximum deviation, just because it gives them a better handle on going from one location to another location, and that they're more exact in the measurement that they're using. But it's the quiet zone that determines the size of the chamber. It's 3 meters from the front of the turntable, and you have to have space behind the antenna and space behind the turntable, and you have to have space on the sides, and you have to have space on the ceiling as well to go to the full 4-meter height that you need to in order to do testing. So now the height doesn't usually vary because you're only going to 4 meters at all times. So if you can clear 4 meters, you've got sufficient height. But if you go from a 1.5 meter quiet zone to a 3 meter quiet zone, you're going to need a wider space on the length and the width, because again, you're extending the length of the chamber itself in order to maintain that 3, 5, or 10 meter measurement that you want to take. And at the same time, you also need to widen it as well in order to make sure that you have clearance between the tips of the turntable and the tips of the absorber. So the size of the chamber is usually dependent and is consistently required to be dependent upon the size of the quiet zone. Does that answer the question?
Yeah, thanks.
We've seen some chamber designs that we've done that go to 6 and 9 meter turntables for EMC testing or emissions measurements of cars and trucks and so forth. And that requires 60, 70 foot chambers. We call mega 10 meters. Those are possibilities. And at the same time, it can go as low as a compact mini chamber, which can usually provide you with a full field uniformity compliance of 1.5 meters by 1.5 meters, but only pre-compliant in that the low frequency range of 30 megahertz to 200 megahertz is maybe plus or minus 6 or 8 rather than 4. But anything over 250 or over a gig is usually plus or minus 4. But it's still a pre-compliant chamber because you can't raise your antenna to the height of the full height of 4 meters. And those chambers usually run in the size of about 12 by 13 by 24, 26 feet long. So again, depending on what your performance expectation is, what your quiet zone size is, what your measurements distance is, those will have an impact on what the size of the chamber needs to be. Anyone else?
Okay,
So
not,
I'm just
not,
wondering, just,
go ahead,
one-
go ahead.
so I'm just wondering if you don't run this test, is there another way to verify your chamber? Something-
Is there another way of verifying the chamber besides NSA, sVSWR, and the magnetic field?
yes.
Um, there was a test procedure which I mentioned earlier in the slides, which is a substitution method. It used to be part of CISPR 25, in which you were able to take measurements of the ground plane on an open area test site that you knew was qualified. You took it on a qualified test site, and then you took it in your chamber. And if they were the same, then you could basically say that your chamber met the requirements. But that's no longer acceptable under CISPR 25. That now requires a long wire test. And I have not yet had a chance to look into the sVSWR requirements on that. But either way, NSA will not allow that. So no matter what, you have to do NSA testing. And I believe that sVSWR requires that you do the testing as well. It's only, I think, on the magnetic field that you might be able to do the substitution method, because I think it mentions it in the standard, but we haven't seen sufficient specifications from the standard yet until it comes out in February, in which case we'll be able to clearly know. But right now, the short answer to the question, which is probably the one I should have given you, is no. You should probably go with exactly what we provided here.
Any more questions?
Should there be any further questions, I'm always open for any phone calls or emails. You're welcome
Yes,
to get
I
in
have
touch
a
with me.
question.
Yes.
So understood, depends on the EUT and so on, chamber sizes are different. Then can I ask, what was the biggest size and the smallest size you ever built?
I would love to say I can answer that question, but I don't know off the top of my head.
Okay.
I
Okay.
apologize. I've been doing this now for the company for 7 years, but they've built even larger than, I mean, I've seen them welded together the size of a building. I've
Ooh, wow.
seen military
Mm.
chambers that are ones where you can walk in and you can roll a helicopter or an airplane inside of it,
Oh,
suspended from the
okay.
ceiling.
Okay.
But the largest size I've seen right now for a 10 meter, I think, is somewhere in the area of like 60 feet by long. I don't remember the width and the height,
Wow.
but usually the height, again, no longer needs to go any higher than 25 feet maximum.
Mhm.
21 feet on the average for a 4 meter height distance. But I've heard of chambers that are so large, you can drive cars into them, as I said.
Yes.
And I know that we have one designed and quoted for that sort of size, a couple of them actually. And I've seen some that you can actually literally drive them in, but I don't know what the largest is offhand that we've built. I'm sorry.
Okay. Okay. No. Thank
I
you.
got stumped. Good question.
That's
Thank you.
no problem. Okay, any further questions before we do the drawing? Stick around for the drawing.
All right. Thank you, everyone.
Yeah, thank you, Lou, very much. And
No
if
problem.
you want to send me the slides, I'll add those in the video.
Sure.
Uh,
And you can give them my contact information if they need to contact me for any questions.
Okay, I'm going to stop the recording now, and then we're going to do the drawing.
Sounds good. Thank you.
Thank you. Let's see here. It's not stopping now. How do I stop it? Request to record. Hopefully it recorded this. Is it still recording? Anybody else got any tips on how to stop the recording?
You're no
wow.
longer the host, Scott, and the host has to stop it.
Oh,
Sorry, Scott, I have it. I can stop it.
okay, stop.